In this playlist, we will look at the most common design patterns. So what are they exactly? Imagine them as battle-tested solutions to recurring design problems. They are like blueprints for solving common issues in software development. Design patterns are born out of the collective wisdom of experienced developers, offering a structured approach to problem solving. Now, let's explore the different types of design patterns. Creational design patterns focus on the process of object creation. Singleton, for example, ensures one class has only one instance. At the same time, the factory method and abstract factory patterns provide an interface for creating several instances of a class. Structural patterns deal with the composition of classes or objects. Examples include an adapter pattern, which allows incompatible interfaces to work together, and a decorator pattern, which lets you add new functionalities to things by wrapping them. Behavioral patterns are all about communication between objects, defining how they collaborate. The observer pattern lets one thing notify others about the state changes, while the strategy pattern allows you to define a family of algorithms and make them interchangeable. Now you might wonder, why bother with design patterns? Well, here is the deal. Design patterns promote code reuse. Why reinvent the wheel when you can use proven solutions? They make your code more maintainable. If a problem arises, you don't have to start from scratch, just apply a relevant pattern. As your project grows, the patterns help maintain a structured and scalable architecture. For all you newcomers, here are some quick tips. Start small. Take your time with every pattern. Begin with the basics and gradually expand your toolkit. Understand context. Each pattern has its place. Understand the problem context before choosing one of the pattern. It's not one size fits all. Use it. Try to apply design patterns in real-world projects. The best way to learn is by doing. In conclusion, design patterns are your secret weapon in software development. They offer elegant solutions to common problems, making your code more stable and maintainable. Whether building a small application or a complex system, the patterns are your trusted allies. Part 1. Creational patterns. Factory method. Imagine a scenario where you have a framework for creating simple text documents. Wherever you need to work with documents, you use the method and functions associated with text documents, and your entire codebase is tightly coupled to text documents. One day, you decide that you need to add the ability to work with the PDF format. You found all the places where you use the text document methods and added conditions to check which of two file formats you are currently using and which function we need to call in which case. A few days later, you decided to add the MOBI and doc formats as well. And now you see the problem. You don't want to add conditions in every place again. And from this point, you want a universal strategy that works with all existing formats and an easy way to add new formats. This is where the factory method design pattern comes into play. The factory method is a creational design pattern used in software development to create objects using a superclass, allowing superclasses to alter the type of object they create. It provides an interface for creating instances of your class, but delegates the responsibility for creating instances to its subclasses. This pattern is typically used to provide loose coupling and flexibility when creating objects. For example, let's define an interface document with methods for working with documents. Then, let's create an interface document factory with the createDocumentFactory method. Then, for each supported document, let's create implementation of the document factory interface and name them, for example, TXT Document Factory and PDF Document Factory. Each of these classes implements the createDocument method to return specific document types. Now, when you want to add a new document format, such as MOBI, you simply create and implement a MOBI Document Factory class that will return MOBI document objects from the createDocumentFactory method, and that's all. Usage is also simple. At the point when you need to interact with the document of specific type, you instantiate the corresponding document factory and later use it to create and manage documents. The code itself will not know exactly which document it's using right now, but it doesn't need to know that, right? There are four main actors in this design pattern. The first one is the factory. Factory is an interface that declares a factory method, responsible for creating objects of a particular type. The next one is Concrete Factory. This is a subclass of factory that implements a factory method for instantiating concrete product classes. The next actor is the product. It is also an interface that defines methods for objects created by a factory method. And the last actor is Concrete Product, a product's subclass that implements the specific functions of the created object. Speaking of benefits, the main one is, of course, the flexibility to introduce new types of products without changing existing client code. What's also good is that this design pattern reduces the coupling between client code and concrete implementations, providing loose coupling, because clients depend on the factory interface rather than concrete classes. Last but not least, the factory method separates object creation from the rest of the code, making it easier to manage changes to the object creation logic. The disadvantages are the following. Creating separate concrete factory classes for each object type can result in more classes and potentially more complex relationships between them. Additionally, if the logic for creating multiple products is similar, you may end up duplicating code across different implementations of a particular factory. Abstract Factory. Imagine that you are developing a video game with a nice world. At some point, you decide to add a completely new fiery world. This means that now we need two different environments, each with its unique characters, enemies, plants, obstacles, and so on. You don't want to tie the creation of certain objects to the worlds, so you want to create some kind of mechanism that takes responsibility for creating the appropriate families of objects in the corresponding worlds. In this game, we can use the abstract factory design pattern for creating objects and entities specific to each world. The abstract factory is a creational design pattern that provides an interface for creating families of related or dependent objects without specifying their concrete classes. It extends the concept of the factory method pattern by introducing multiple factory methods organized into a single abstract factory class. This pattern is especially useful when a system needs to be independent of how its objects are created, composed, and represented. First, let's create a world factory, which is an interface that defines methods for creating different types of objects in the world. Concrete implementations of world factory create objects specific to ice and fire worlds. Let's call them Ice World Factory and Fire World Factory. Each of these concrete factories will implement all the world factory methods and return specific objects corresponding to their world. Now, when you want to add a new world, such as Air World, you simply create and implement an Air World Factory class that will implement each world factory's method, and that's it. Then, you will be able to use this new world's factory and there will be no changes in the existing worlds. If you want to add a new game entity to all worlds, you simply add the function to the world factory and implement it in each specific factory. This addition will not break existing code, and after that, you will be able to use the new entity in your new scenarios. There are 4 actors in this design pattern. First, Abstract Factory. This is an interface that declares several factory methods and is responsible for creating a family of related products. Concrete Factory is a subclass of Abstract Factory that implements factory methods to create concrete instances of related products. The last 2 actors are Abstract Product and Concrete Product. Concrete Product is a subclass of Abstract Product, which is an interface that implements certain product features defined in Abstract Product. The Abstract Factory design pattern offers several advantages. Firstly, it promotes consistency by ensuring that the products generated by the factory are compatible and consistent with each other. Secondly, it enables the isolation of object creation. This means that client code remains isolated from the specifics of object creation, contributing to a high level of abstraction. Also, the Abstract Factory pattern offers flexibility. You can easily introduce new product families by creating new concrete factory classes without changing existing client code. Lastly, it encourages separation. Clients rely on the abstract interfaces of factories and products, which reduces dependency on concrete classes. Speaking about disadvantages. Firstly, it can introduce increased complexity to the codebase, particularly when managing multiple factories and product families. As more types of product and factories are added, the number of classes and interactions can grow substantially, potentially making the code harder to understand and maintain. Secondly, the Abstract Factory pattern has a limited scope and is most suitable when dealing with a specific set of related product families. If the application requires creating individual objects with unique characteristics, other creational patterns like factory method or builder might be more appropriate. Builder. Imagine that you are building an application where the user can craft and order custom pizzas with a predefined list of ingredients. When a user creates a product, you want to show the final state on the screen so that the user can approve their order. This particular feature can be implemented using the builder design pattern. The builder is a creational design pattern that separates the construction of a complex object from its representation, allowing the same construction process to create different representations. It provides a way to incrementally create objects, allowing you to create complex objects with different configurations, while keeping the construction code separate from the final structure of the object. The pattern is especially useful when creating objects with optional or variable components. Let's create a product builder that contains all the methods we can apply to product. In our case, these are add dough, add tomato, add cheese, add pepperoni, etc. After that, we can create concrete builder to implement the product builder interface, the pizza builder. It works with their specific product, pizza. Now, we are ready to create a specific product. When the user selects the product they want, we will create a new instance of pizza builder. We then will add all the ingredients selected by the user to the product and get a built product that we can already draw on the screen. Concrete builders know how to apply those specific ingredients to their product and how to build it at the end. There are three actors in this design pattern. Let's start with builder, which is an interface that declares methods for building the various parts of a complex object. Then, concrete builder, a subclass of builder that implements methods for building individual parts of a complex object. The last actor is the product. It is a complex object being constructed, typically composed of multiple parts. The design pattern offers several benefits. Firstly, it promotes the separation of concerns, effectively segregating the build process from the client code. This separation simplifies the management of complex object creation and representation. Secondly, builders enhance configurability, enabling the creation of objects with various configurations while reusing the same building process. Lastly, the pattern enhances code readability, as client code primarily concentrates on high-level object construction rather than delving into detailed construction steps. This design pattern offers several advantages, but it also comes with some disadvantages that need to be considered. One significant drawback is the increased code complexity it introduces. This complexity arises from the creation of multiple classes and interfaces, which can make the overall codebase more intricate. This can be especially problematic for smaller projects where the benefits of the pattern might not be fully realized. Another potential disadvantage is the risk of inconsistency. This arises because the pattern involves constructing an object step by step. If the builder is not used correctly, there is a possibility of introducing inconsistencies. For instance, forgetting to set a required property or setting properties in the wrong order could result in objects that are in invalid or unexpected states. Prototype. Imagine you are building a graphic design application with several types of visual elements, such as circles, rectangles, and triangles. Each of these graphics can be placed on a layer. Then, this newly created layer can be placed on another layer, and so on. You are working on a copy-paste feature, which means you want to be able to select a graphic element or layer and copy-paste it with all the layers and elements it contains. Of course, you can recreate all objects and layers from scratch, but this can be too complicated and expensive. So, you want to be able to duplicate the entire structure, and for that, you can use the prototype design pattern. The prototype design pattern is a creational design pattern that allows you to create new objects by copying or cloning existing ones. It focuses on constructing new instances by duplicating existing ones, minimizing the object creation overhead. So, let's start by creating a top-level graphic prototype interface with the clone method. Graphic elements such as circle, rectangle, and triangle are subclasses of graphic and implement the clone method to create copies of themselves. Additionally, layer is subclass of graphic and is just an array of other layers or graphic elements described above. Its clone method calls the same method for each layer and graphic element it contains, combines it, and returns a new layer. When the user wants to duplicate a layer, the client code calls the clone method on the corresponding prototype. There are only two actors in this design pattern. The main interface prototype defines a clone method, and concrete prototype, a subclass of prototype, implements the clone method to create its copies. The prototype design pattern provides a range of advantages and disadvantages for object creation and management. Enabling the cloning of objects reduces the overhead associated with recreating and initializing objects from scratch significantly. This results in more efficient and streamlined process, especially when object initialization is resource-intensive. Additionally, the prototype pattern enhances the flexibility of the development process. Developers can create new object instances simply by cloning existing prototypes. This ability to generate new objects on the fly contributes to a more agile and adaptable development environment. Despite its advantages, the prototype pattern has its challenges. One of the main disadvantages lies in the potential for circular dependency issues. Implementing the prototype pattern can become complex and tricky if the object that needs to be cloned has a circular dependency. This situation requires careful handling to ensure that the pattern is implemented effectively without introducing bugs or inconsistencies in the application's behavior. Singleton. Imagine that you are creating a game and you are working with some assets, such as textures, sounds, models, and so on. You have an assets manager that helps you easily retrieve and work with these assets. Right now, you instantiate and use the manager's instance in every game scene, and even in every game script. And because of this, the resources are loading every time. You realize that if you already load some resource, then most likely you want to use it again in the near future, so there might be a good reason to cache those assets for future use. But in our current code, creating the manager every time is a problem, because the resources are not cached and we can't reuse them. This is where the Singleton design patterns comes in handy, and can help us create a manager just once and take advantage of caching everywhere. Now, let's talk about Singleton itself. The Singleton design pattern is a creational design pattern that ensures a class has only one instance and provides a global access point to itself. Singleton ensures that a single instance of a class is created and shared throughout the life of an application, which prevents multiple instances from being unintentionally created. Let's create an Assets Manager class that will be the main actor of the Singleton design pattern. It should not have any public constructors to create itself, only the static method named getInstance should do it. The user should call this method to receive an Assets Manager instance, and after that, they can use any non-static method with it. The user will not know anything about caching or internal optimizations, because this logic will be encapsulated in the Assets Manager class. There is only one actor in this design pattern, the Singleton itself, which is a class that implements the Singleton pattern, ensuring that only one instance of it can exist. The Singleton design pattern offers several advantages. One of the key benefits of the Singleton pattern is providing a single, well-defined access point to an instance, ensuring global access and making it easy to manage and use throughout the application. This design pattern also excels in resource management, as it can control the allocation and release of resources, guaranteeing their efficient use. Furthermore, a Singleton is capable of maintaining a unique state within an application, which is particularly useful for storing configuration settings or shared data that need to be accessed by various components. Additionally, the Singleton pattern can support lazy initialization, meaning that the resources can be loaded on demand. This improves performance by deferring the load of the resources until it is needed. Despite its benefits, the Singleton pattern also has its drawbacks. Testing can become a challenging task due to tight coupling and global nature of a Singleton, making the codebase difficult to test. In multi-threaded environments, there is an added complexity, as the creation of a Singleton must be thread-safe to prevent race conditions, ensuring that the instance is created only once, even when multiple threads attempt to create it simultaneously. In general, Singleton is mostly seen as an anti-pattern because it adds complexity to the code and is very difficult to reuse or test. Eliminating singletons can be a challenging task, but it is an effort that pays off in the long run. Part 2. Structural patterns. Adapter. Imagine that you are building a website that needs to collect and aggregate currency rates from different banks and display them beautifully on a web page. Each bank has its unique API, so you want to design your application so that adding a new banking API is a simple task. Also, if some banks decide to change their API, you certainly don't want to break other API's code. You want a unified source of information, so you need to adapt the information banks provide. Did I say adapt? Yes, so let's use the adapter design pattern here. The adapter is a structural design pattern that allows objects with incompatible interfaces to work together by providing a bridge between them. It acts as a translator, allowing two classes with different interfaces to communicate and collaborate seamlessly. First, let's create the bank interface. Here, we have methods getRate, getCurrencies, getBankName, and so on. Next, we will create an adapter class for each bank we need, and call them Bank1 adapter, Bank2 adapter, and Bank3 adapter. Each of these adapters must work with its bank and convert its incompatible interfaces to our unified interface. When we want to add a new bank, we need to add a new adapter class for that bank and use it like the others. Also, if some banks decide to change their API, which breaks their adapter code on your site, you can properly handle this situation or ignore the broken bank APIs. There are three actors in this design pattern. First, target is an interface that the client's code expects to work with. Then, adaptee is a class with an incompatible interface that must be adapted to work with the client code. And finally, the adapter itself. This class implements the target interface and interacts internally with the adaptee, translating calls and operations as needed. The adapter design pattern offers a range of benefits. It enables classes with different interfaces to work unitedly, significantly aiding in code reuse and seamless integration. This pattern ensures that disparate systems communicate effectively, enhancing the application's overall architecture. It also promotes a clear division between the client code and the complexities of external API. This separation fosters modularity, making the system more manageable and easier to navigate. The adapter proves to be invaluable when it comes to integrating pre-existing legacy code into new and evolving systems. It ensures a smoother transition and enhanced compatibility. While the adapter pattern offers numerous advantages, it also introduces an additional layer of complexity to the codebase. The added complexity can lead to challenges in understanding and maintaining the code, particularly for those unfamiliar with the design pattern. The adapter's additional layer can result in performance overhead, the next potential disadvantage. It could slow down the system, particularly when high efficiency and speed are crucial. Additionally, the adapter pattern may require significant effort to implement when dealing with complex interfaces or APIs. Further, it may only sometimes yield a clean and elegant solution, potentially leading to imperfect results in terms of code clarity and functionality. Bridge. Imagine that you are implementing a text editor, and your current task is to design and implement a plugin system. Plugins are small and primarily implemented by the community programs that take an editor's context and manipulate it. The main goal is that the text editor and plugins can develop independently without blocking each other. The bridge design pattern is perfect for this purpose. The bridge is a structural design pattern that separates abstraction from implementation, allowing them to evolve independently. It decouples an abstraction's interface from its implementation, allowing changes in one without impacting the other. This pattern is handy when dealing with complex class hierarchies, and when changes in both abstraction and implementation are expected. First, let's create a plugin system interface that has a single method that takes a plugin as an argument. Then, let's define an interface each plugin must implement and call it plugin. It has a single apply function that accepts an application's context and will be called from the register new plugin method. When a particular plugin is created, we must call the register new plugin method with it, and then its apply function will be called from register new plugin. The apply function can now manipulate the context, add context menus, change the text, add callbacks, and so on. As you can see, we ended up with a design with two parts in our architecture, one for our application and one for plugins. Both of these parts can be developed separately, and neither of them will block the progress of the other. There are three actors in this design pattern. The first is abstraction, a high-level interface that defines methods and properties for implementation and keeps a reference to the latter. The next one, implementation, is a low-level interface that defines the method and properties to be implemented by concrete classes. Concrete implementations are subclasses of implementation that provide the actual implementations. The bridge design pattern comes with various advantages. It offers a significant level of decoupling between abstraction and implementation. This means changes can be made to either side without impacting the other, making system maintenance easier. Additionally, the pattern facilitates extension, allowing new abstractions and implementations to be added independently without much fuss. On the flip side, it can introduce additional complexity to the system, particularly when there are multiple levels of abstraction and implementation. Furthermore, in scenarios where the system is quite simple, employing the bridge pattern might lead to unnecessary overhead, unnecessarily complicating both the code and the overall design. Composite. Imagine that you are working on a website that hosts many different computer science and competitive programming problems. You want to create a framework to generate random tests for these problems. You want to be able to specify limits for each test element and then generate an infinite number of tests. Let's look at an example. Imagine a problem where the input is an array of strings followed by two numbers. The string length must be between 1 and 10, and array's length must be between 2 and 5, and the numbers must be between 1000 and 10,000. You want to be able to specify these limits to get an infinite number of different tests. The composite design pattern is what you are looking for. The composite is a structural design pattern that combines objects into tree structures to represent part-whole hierarchies. It handles individual objects and object compositions uniformly, allowing clients to work with complex structures and particular objects using a single interface. Let's create a test interface with a single generate method. Then, let's create a range class that implements the test and accepts a range of possible values. After that, let's create a string class that implements the test interface and accepts the range in the constructor. Now, let's create an array class that also implements the test interface. An array accepts the range, and an object reference it must contain. Also, to compose all these classes, we need to create a composite test, which implements the test, stores an array of the test objects, and has an addTest method. With this class's help, we can now generate multiple random tests in the format we described earlier in the video. First, let's create a string and pass it a range 1 to 10. Next, let's create an array that will accept a range from 2 to 5 and the string we just created. Then, let's create two numbers ranging from 1000 to 10,000. And finally, let's create a composite test and add an array and two numbers to it. Since the composite test inherits the test interface, it can use its generate method to create the entire test. When a client calls the generate method, composite test calls generate for each test element it contains, then they do the same. At some point, the process will reach so-called leaf nodes with no containing elements. In our case, composite test will call generate on the array and numbers. The numbers will return instantly, but the array has to generate the numbers from the range, get the number of strings it should contain, and then call generate that many times on the original string. There are three actors in this design pattern. The first one, component, defines a common interface for leaves and composite nodes. Leaf and composite are classes that both implement the component interface. But the first one represents the individual object in the composition, while the second represents the composition itself and contains a set of child components. One of the main advantages is its unified interface. It provides a consistent way to work with individual objects and complex compositions. This consistency simplifies client code and enhances ease of use. Moreover, its recursive structure is beneficial for representing complex hierarchical structures in a clean and organized manner. Additionally, the pattern is highly flexible, allowing the incorporation of new components, be they leaves or composites, without any destructive effects on the existing structure or client code. However, this design pattern has its challenges. The introduction of the composite pattern can lead to increased complexity, particularly in the situation involving deeply nested hierarchies. Operations performed on composite objects may require traversal through the entire hierarchy, potentially leading to performance issues. Furthermore, in simpler scenarios, applying the composite pattern may result in unnecessary overhead, complicating the code and the overall design. Decorator. Imagine creating a game with a hero with several properties, such as attack, health, speed, and so on. You want to reward the players with some property upgrades during the gameplay. These upgrades have a similar structure, such as get +5 attack, or get plus 20% of speed, or get double jump, or get bow, and others. You want to make these upgrades modular and apply several sequentially to different properties. This is where the Decorator design pattern comes in handy. The Decorator is a structural design pattern that allows you to dynamically add behaviors or responsibilities to objects without changing their code. It involves creating a set of Decorator classes to wrap specific components, add new functionalities, or runtime behaviors. Let's create an interface character. This interface has all the necessary methods to control the hero, such as attack, take damage, move, jump, and so on. Next, let's create a default character class that implements the character interface and provides a default hero implementation. After that, let's create an upgrade interface that extends the character interface and will be used for the concrete implementations of upgrades. And finally, let's create classes that implement the upgrade and call them attack upgrade, speed upgrade, health upgrade, double jump upgrade, and so on. Each of these classes must implement all methods from upgrade, accept character in the constructor, and add their specific logic to the implementation. When upgrading a character in the code, you can wrap the current character and work on the new object as before, since the upgraded character is still a character. There are 4 actors in this design pattern. A component defines a common interface for concrete components and decorators. Concrete component class implements the component interface and provides basic functionality that decorators can enhance. We then have the Decorator, an interface extending from component. It maintains a reference to the component instance. And concrete decorators are subclasses of Decorator that add specific behavior or responsibilities to a component. In terms of advantages, it adheres to the open-close principle, as it allows for extending objects' functionalities without altering their existing code. This ensures the system is open for extension but closed for modification, promoting a robust and flexible design. Also, it supports the addition and combination of various decorators at runtime. This results in a dynamically changing system and flexible behavior extensions. Furthermore, the pattern encourages a separation of responsibilities. This approach enhances the maintainability of the code, making it easier to manage and update. On the flip side, one of the primary challenges is the complexity it introduces, resulting in an increased number of classes. This can make the codebase more intricate and challenging to grasp, especially for newcomers or those unfamiliar with the pattern. Additionally, the order in which decorators are applied is crucial, as it can significantly impact the system's behavior. If not managed carefully, this could lead to unexpected results, potentially creating bugs or issues within the application. Facade. Imagine that you are implementing a social network application in which users have profiles. A profile can contain various information: name, email address, profile picture, friends list, and recent posts. A separate service is responsible for the posts, another for friends, and another for storing the user's name and email information. Thus, to display a profile, the client must make a call to obtain the email, name, and image data, then request the list of friends and the posts. Later, you must add more services based on user interests, recently visited places, etc. This approach makes it more challenging to find the data, because for each type of data in the profile, the client must know where to get it from. It would be much more convenient if all the necessary data for displaying a profile were received simultaneously. This is where the facade design pattern comes into play. The facade is a structural design pattern that provides a unified interface to a set of interfaces in a subsystem. It simplifies complex systems by offering a high-level interface that shields client from the complexities and interactions of individual components within a subsystem. The facade pattern is especially useful when working with complex systems or third-party libraries, where a simplified interface can improve usability and hide implementation details. Let's define the user profile provider interface that the client will use and which contains a method getUserProfile. Then, let's create a user profile provider impl class that implements the interface. Its method returns all the information about the user's profile. It hides the complexity of obtaining information from various services, such as friends provider, host provider, and so on. When new data needs to be added to the profile, the interface method and its use should not change. There are three actors in this design pattern. Facade provides a simplified interface to a subsystem. The facade impl implements facade and manages the interaction with subsystem classes and hides their complexity. Subsystem classes are separate classes that make up a complex system. Clients can interact with these classes directly, but it's more convenient to use a facade. On the positive side, it greatly simplifies usage by offering a single entry point to a complex subsystem, making it easier for clients to interact with the system. This is beneficial as it reduces the effort required from the user's end. Additionally, it encourages separation between clients and subsystem classes, resulting in loose coupling and simplifying the maintenance process. Furthermore, a design pattern provides a well-organized and clean method to encapsulate subsystem functionalities, offering clients a cleaner and more user-friendly API. One of the main disadvantages is that it can reduce flexibility, as implementing a facade might make it challenging to modify or expand individual subsystem components without impacting the facade itself. This is a significant consideration, as it could lead to complications in the long run. Another downside is the potential for a bloated interface. As the subsystem evolves and grows, the facade interface might become overloaded with methods to meet different clients' diverse needs. This can make the system cumbersome and less efficient. Flyweight. Imagine that you are developing a strategy game, and you want to create large-scale battles with thousands of units on the screen. At first, it may seem that there is no problem and no place for design patterns. But wait, let's calculate how much memory your game will use for these battles. Units in the game have many different parameters, but let's take a look at the unit's sprites or textures. Let's assume that the size of one sprite is 1 MB. If there are 1000 units on the screen, then 1 GB of memory will be used only for essentially the same textures. Here's an excellent place to optimize the memory usage, and as you might have guessed by now, we can use a design pattern here. The flyweight in this case. The flyweight is a structural design pattern that focuses on efficiently sharing and reusing object states, especially when many similar objects need to be created. It aims to minimize memory usage by sharing a common state across multiple objects, reducing the application's overall memory footprint. Let's create a class and call it Buildings Factory with two methods, getArcheryRange and getStable. These two methods must accept the common state of the unit, such as sprites, speed, types, etc., so that Buildings Factory can understand which archery and which stable it should return. Each building has one method, createArcher and createHorseman. These methods must receive unique to each unit state, such as their position, rotation, etc. Buildings can then return new units to the client, ensuring that the units reuse their repeating state. There are three actors in this design pattern. First of all, Flyweight Factory. This is a class that contains methods for getting all available Flyweight classes. The Flyweight class is responsible for managing and creating Flyweight objects. It ensures that the shared state is reused. And objects are the classes that Flyweight creates and contain repetitive information that we are trying to optimize. On the positive side, Flyweight is highly beneficial for improving memory efficiency, as it enables the sharing of repetitive states across multiple objects, which is particularly useful when there are many instances of an object. This not only helps reduce memory consumption, but also enhances the application's performance by minimizing the overhead associated with creating and destroying objects, especially in resource-intensive scenarios. Additionally, Flyweight aids in resource management by centralizing the control and management of the life cycle of shared objects, making it easier to handle them efficiently. However, there are also disadvantages to consider. The Flyweight pattern can introduce a level of complexity, especially when managing extrinsic states that cannot be shared and need to be handled separately. This can make the implementation more challenging and lead to errors if not managed correctly. Additionally, because the Flyweight pattern involves sharing intrinsic states among objects, it might limit the extent to which individual objects can be customized, reducing flexibility in specific scenarios. Finally, there is a trade-off between sharing and duplication that needs to be carefully considered to ensure the correctness of the application. Deciding which state should be shared and which should remain separate is critical to implementing the Flyweight pattern. It requires serious evaluation to make the right choices for the specific use case. Proxy. Imagine that you have created an API to generate images from a text description. At first, everything was fine, but at some point, you noticed that some client was making a huge number of requests to your API, which caused your system to crash. You temporarily suspended this user's account and restored the system. But now you want to create a kind of a shield to prevent users from making so many requests. The proxy pattern will help you with this. The proxy is a structural design pattern that provides a placeholder for another object to control its access. It acts as an intermediary, allowing you to add additional behavior or control to the original object without modifying its code. Proxies are commonly used for various purposes, including controlling access, managing resources, and delaying object creation. Suppose you have an interface for your API call. Let's call it Generate Image Interface, and an implementation that receives the client's request and does the actual image generation. Let's call it Generate Image Impl. Now, let's create another implementation of Generate Image Interface and call it Generate Image Rate Limiter. This rate limiter accepts and stores an instance of the impl class to redirect the call when the rate is not exceeded. Otherwise, when the rate is exceeded, this class becomes a lightweight shield that will prevent the heavy work from starting and will immediately return an error to the client asking to repeat the same request after a delay. In practice, you don't need to create a unique rate limiting proxy for each specific class. There is a general solution that can also be in a different network layer, so your server will not be overloaded due to requests that should be rejected immediately. There are three actors in this design pattern. The first, subject, is a generic interface that defines both methods, the real subject and the proxy implement. This allows you to use a proxy instead of a real object. Real subject is a class that represents the real object or service that the proxy controls access to. And of course, proxy, a class that implements the same interface as the subject. It contains a reference to the real subject and controls access to it, adding any necessary functionality. In terms of benefits, the proxy pattern enhances access control by enabling you to manage the permissions and access to the real subject, adding an extra layer of security or authorization. This can be particularly crucial in scenarios where sensitive information or operations are involved. Additionally, it aids in efficient resource management as proxies have the ability to handle resources related to the real subject. This contains lazy initialization, caching, and releasing resources when they are no longer necessary, contributing to a more optimized use of system resources. Furthermore, proxy can optimize the performance of the system. For example, it can postpone the creation or execution of resource-heavy objects or tasks, or reuse just calculated results. Lastly, the client code becomes simpler and more straightforward when using the proxy pattern. The complexity of functionalities or interactions is encapsulated within the proxy, making it easier for the client code to interact with the real subject. On the other hand, there are some disadvantages to consider. The introduction of the proxy pattern can lead to increased complexity in the system. This is particularly evident when managing various types of proxies and understanding their interactions, which can become a challenging task. Moreover, as proxies add an extra layer of indirection, there is a potential for a slight performance overhead, though this is typically outweighed by the performance benefits in most scenarios. Part 3. Behavioral patterns. Chain of responsibility. Imagine that you are building a service that various websites can use to create rules for their password policy. Some companies may require at least 10 characters in the password. Some may block hyphens in passwords, and others may require the password to contain at least 2 special characters. You want to design your service so that your clients can create their own rules, easily chain them, add new ones, and change the order of the rules. Like I said, it's a chain of responsibility. The chain of responsibility is a behavioral design pattern that allows you to create a chain of objects, where each object can either handle a request or pass it along to the next object. It decouples the sender of a request from its receiver, enabling multiple objects to handle the request without explicitly specifying which object will process it. In our case, we are using a slightly modified version of the chain of responsibility. We have the chain in which a password must pass each object's validation to become a valid password. Therefore, each object must process the password and pass it along the chain if the processing is successful. Let's create an interface and call it rule. It has a single function named validate. Then let's create some real rules like minimum length rule, maximum length rule, special character prohibiting rule, and so on. Each rule contains a reference to the following rule, which we provide in the constructor, so each one of them can continue the chain of calls if its own rule succeeds or breaks the chain if not. Clients can create chains, mix them up, create rules by parameterizing existing rules, and get any password patterns they want. That's it. This design pattern has 2 actors, handler and concrete handler. The first is an interface that defines a common interface for handling requests. It contains a reference to the next handler in the chain. Concrete handler is a subclass of handler that implements special request processing logic. A classic design pattern can either process the request or pass it on to the next handler in the chain. In our variation, it should do both, process the request and pass it to the next handler. One of the most significant advantages is decoupling, as it separates the sender and receiver. This separation allows for modifications or the addition of handlers without any need to alter the client code. In terms of flexibility, the design pattern shines, providing a dynamic and adaptable method for processing requests. Handlers can be effortlessly added, removed, or rearranged, facilitating easy modifications to suit changing requirements. Furthermore, each handler in the chain of responsibility focuses on a specific task, adhering to the single responsibility principle and resulting in better organized and more maintainable code. On the flip side, the design pattern has its disadvantages. One issue that may arise is order dependency. The sequence of handlers in the chain plays a crucial role, and any misplacement might lead to bugs or unexpected outcomes. Another potential drawback is the risk of requests going unprocessed. If a request traverses the entire chain without being addressed, it remains pending, which could pose problems depending on the application's context. Additionally, since every request has to pass through all the handlers, it could introduce a performance overhead, especially if the chain is lengthy. Command. Imagine that you are working on a brand new online drawing tool where a user can perform actions like draw, erase, resize, etc. You want to design your application so that each action the user performs can be reversible. Also, you like to be able to bring back the reversed action in case you reverse it by mistake. These operations are known as undo and redo, and you can use the command design pattern to implement them properly. The command is a behavioral design pattern that turns a request into a standalone object, containing all information about the request. This decoupling allows for parameterizing clients with different requests and supports undoable operations. Let's create an action interface that has a single execute method. Then, let's create concrete actions like draw, erase, resize, etc. Each of these classes inherits the action interface and implements their logic in the execute function. Then, let's create an application that is responsible for creating actions. Also, let's make the canvas on which the commands should be performed. Now, let's see the flow. When the user is performing the action, the application creates a concrete command, stores it in command history and executes it. The concrete command performs changes on the canvas. When the user wants to undo their action, you must discard the last action from the history. For the redo operation, you need to return just discarded action or do nothing if no such command exists. To implement this, you can use a pointer to point to the last correct action without deleting or maintaining another history of throughout actions. There are 4 actors in this design pattern. The command defines the common interface for all concrete command objects. It usually includes an execute method. The concrete commands are subclasses of command that encapsulate a specific action by binding a receiver to the action's execution. The invoker class holds and manages the command objects. It triggers the execution of commands through the execute method. And finally, the receiver is a class that performs the actual action associated with the command. It knows how to carry out the operation. In terms of benefits, this design pattern promotes decoupling between the sender and the receiver, leading to more flexible interactions and straightforward maintenance procedures. Additionally, command objects are capable of storing state, which facilitates the implementation of undo and redo operations, a significant advantage for user experience. However, this design pattern has its drawbacks. One major disadvantage is the potential for increased complexity within the codebase. Multiple command classes can make the system more challenging to understand and navigate. This is closely related to the issue of class proliferation, where the need for various actions could result in an overwhelming number of command classes, further complicating the code structure. Sometimes, the command design pattern might be considered overkill, making the code less intuitive and more challenging to grasp, especially for simpler actions or scenarios. Interpreter. Imagine you are building a calculator app allowing users to enter some basic math expressions. Right now, you only want to implement plus, minus, and parentheses, but you will definitely want to add other operations in the future. Your expression language may be more challenging at some point, so you want your application to be well designed. Here, the interpreter design pattern is a good choice for you. The interpreter is a behavioral design pattern that provides a way to evaluate sentences or expressions in a language. It defines a language and its grammar in terms of a set of classes, where each class represents a rule or production of the language. This is useful when creating an interpreter for a simple language or expression, such as regular expressions, mathematical expressions, or domain-specific languages. Let's start with the math expression interface with a single calculate method. Then, we will create 4 different classes inherited from math expression: plus expression, minus expression, brackets expression, and number. The first 2 classes will contain 2 math expressions, because each of those classes is a binary operation. That is, we need 2 operands to perform our action correctly. Their calculate function calls the evaluation on both math expressions, and then returns their addition or subtraction. The bracket expression class contains 1 math expression and is used to group multiple math expressions into one. Its evaluation method returns the result of the calculate method of its single math expression. The last class, number, contains a number, and its calculate method returns exactly that number. You can easily interpret any expression containing plus, minus, and brackets using these 4 classes. Now, to add new operations, you can add new classes representing this operation, and the overall structure will not change from this. There are 3 actors in this design pattern. The first, abstract expression, or math expression in our case, is an interface that declares an interpret, a method used by concrete expressions to interpret the input. In our example, interpret is calculate. Terminal expression is a subclass of abstract expression that implement the interpret method for terminal characters in the grammar. In our case, it's just a number. Terminal means that this class does not contain any other abstract expression. The last one, non-terminal expression, is also a subclass of abstract expression that implements the interpret method for non-terminal characters in the grammar. It usually combines and interprets multiple terminal and non-terminal expressions. In our example, non-terminal expressions are plus expression, minus expression, and brackets expression. One of the main benefits of this design pattern is its modularity. It breaks down complex grammars into modular expressions, resulting in a more organized and maintainable codebase. This modularity also contributes to the system's extensibility, making it easier to change existing grammar or add new language constructs by adding or modifying expression classes. However, despite these benefits, the interpreter has one significant limitation. Its applicability is restricted, as it is most suitable for scenarios where there is a need to create an interpreter for languages, expressions, or grammars. There also can be more efficient choices than this pattern for more complex scenarios. Iterator. Imagine that you are working on a music application. Your current feature is the next song, and of course, the previous song. In the beginning, you thought that this was an easy problem, but you realize that the application's user has several orders to select the songs. For example, next in list, random, alphabetically sorted, sorted by length, and so on. For this task, the iterator design pattern is the best. The iterator is a behavioral design pattern that provides a way to access elements of a collection without exposing its underlying representation. It abstracts the traversal process, allowing clients to navigate through elements sequentially without knowing the details of the collection structure. First, we should have an interface that defines the collection of songs and has the createWalker method. Let's call it just songs. Then, let's create the walker interface with hasNext and next methods. After that, let's create the concrete walkers, classes that are implementing the walker, for example, random order walker, simple order walker, and sorted by name order walker. Each walker knows their specific way to iterate over the song collection. Finally, we can create concrete collections of songs by implementing the songs interface and using the desired iterators, the random songs, the simple order songs, and sorted by name order songs. When the user selects their favorite order, you instantiate the appropriate collection, and this collection knows how to walk over songs the user has. There are 4 actors in this pattern. The first one, Iterator, is an interface that defines the methods for traversing a collection, including operations like next and hasNext. Concrete Iterator is a class that implements the iterator interface and provides the actual traversal logic for a specific collection. Then, we have the collection, an interface that defines methods for creating an iterator. And lastly, Concrete Collection is a class that implements the collection interface, providing the actual collection of elements and creating an appropriate iterator. Starting with the benefits, the iterator introduces a notable level of decoupling, effectively separating the traversal logic from the collection and ensuring a clean division of responsibilities. This separation enhances the maintainability and scalability of the code, as changes in the traversal logic or the collection structure do not affect each other. Additionally, the iterator pattern provides a uniform interface, ensuring a consistent and straightforward way to access elements across different collections. This uniformity significantly simplifies the client code, making it easier to manage and understand. Another advantage lies in the pattern's ability to handle iterating over complex data structures. This ensures that the complexities involved do not burden the client, allowing them to concentrate solely on their tasks. Furthermore, the pattern supports the implementation of multiple iterators on the same collection, each providing a unique perspective of traversal. This feature is handy when different views or traversals of the data are required. On the other hand, the design pattern is not without its disadvantages. One of the main drawbacks is its limited functionality. The iterator provides just a basic set of traversal methods. This limitation is insufficient to cover all potential use cases that may arise. Additionally, there is the issue of code overhead. The need to implement custom iterators and aggregators can lead to additional complexity in the code. This factor becomes especially visible in simple scenarios where such complexity may not be justified. Mediator. Imagine that you are developing an application on a mobile phone that is a smart home system. Your application should connect to various devices like lights, heating, air conditioning, security cameras, and so on. All these devices should be able to interact with each other. Still, direct communication between these components can lead to a tangled web of interactions, which is hard to manage and maintain. To solve this problem, we can use the mediator design pattern. The mediator is a behavioral design pattern that facilitates communication between different objects without them necessarily being aware of each other or having direct coupling. Their interaction is handled by a central point, the mediator. First, let's create the manager interface, which has a signal method and stores all device references. Then, let's create the class Smart Home Manager, which implements Manager. It contains several functions that are needed to handle different devices. Then, we have a device interface for all the devices we will have. It also includes a reference to the manager. And finally, concrete devices: light, heating, air condition, and so on. With this setup, any device can send a signal to the manager, which will handle it properly. Also, the manager can propagate that signal to all the devices that signal needs. There are 4 actors in this pattern. The first, mediator, is an interface that defines the communication methods that concrete mediators must implement. It also maintains references to the participating objects. The concrete mediator class implements the mediator interface and manages the interactions and coordination between the participating objects. Component is an interface that defines the communication methods that concrete components must implement. It maintains a reference to the mediator. And of course, concrete components are classes that implement the component interface and communicate with the other components through the mediator. Regarding benefits, the design pattern promotes loose coupling and easier maintenance by reducing direct dependencies between components. This centralized control helps manage complex interactions and avoids tangled relationships among components. Also, adding new components or changing interaction patterns becomes easier, with modifications being localized to the mediator, enhancing extensibility. On the other hand, one of the main issues is the additional complexity it can introduce, particularly when dealing with many components and intricate interactions. The mediator can become a single point of failure or a performance bottleneck if it becomes overly complex or tightly coupled with the components. This design pattern also limits the independence of the components, since they need to communicate through the mediator, which is only ideal in some scenarios. Additionally, depending on how it is implemented, using a mediator might introduce a slight performance overhead due to the additional layer of communication required. Memento. Imagine you want to implement your version of the famous 2048 game. You have a 4x4 matrix. Some cells contain powers of 2, and you have to join the same powers by pressing the arrow buttons on your keyboard to eventually get a 2048 tile. And as a killer feature, you want to add game replays. The definition of them is as follows. After the end of the game, a player receives a link through which the friends of this player can watch the entire progress of the current game. Now, you want to find an efficient way to create and store all the steps the player has taken. Memento is a good pattern for this. The memento is a behavioral design pattern that captures and externalizes the internal state of an object without breaking its encapsulation. It allows you to save and restore the state of an object, providing the ability to undo or roll back changes and also save a history of the state of an object. Let's add save and restore functions into our game class. The save function returns a state object containing all information about the game's current state. The restore function takes this state and restores the game to that state. Let's also create a game manager responsible for getting and storing the states of the game on each player's move. When the game ends, you will have an array of game states. With that array, you can replay the entire game from start to finish. Besides replay, with this design pattern, you can quickly implement the undo-redo feature, which we already discussed in the command design pattern. There are only 3 actors here. Originator is the class whose state needs to be saved and restored. It creates Memento objects to capture its state and can restore its state from the Memento. Memento itself is also a class that stores the internal state of the originator. And Caretaker is a class that stores and manages mementos. It requests mementos from the originator and can use them to restore the originator's state. The Memento design pattern enables preserving and restoring an object's state, thereby facilitating undo and history functions. This proves especially beneficial for objects requiring undo-redo capabilities or a state history record. However, this design pattern has its drawbacks. One of the primary disadvantages is the potential for increased memory consumption. This is particularly true for objects with intricate state structures, as storing their state history can be memory intensive. Nonetheless, it is worth noting that there are memory optimization strategies that can mitigate this issue. For instance, in our example, there is a clever optimization technique that allows the entire state of a game to be stored in a single 64-bit number. Reflecting on and devising such optimizations could be an intriguing challenge. In addition to memory consumption, the Memento design pattern can also introduce performance overheads. Creating and managing mementos may lead to a degradation in performance, especially for objects undergoing frequent state modifications. Moreover, the applicability of the Memento design pattern is limited. While it offers significant value for objects that demand undo-redo functionalities or a history of state changes, implementing this pattern may be excessive for simpler objects. Observer. Imagine that you are developing a video game. Your current task is to create a passive skills system in this game. These passive skills should automatically activate on specific events like movement, health changes, or other game dynamics. To efficiently manage these interactions and ensure that skills are activated at the right moment, we can use the Observer design pattern. The Observer is a behavioral design pattern that defines a one-to-many relationship between objects, where changes in one object are automatically communicated to and reflected in other objects. It enables a loosely coupled and efficient communication mechanism between components. First, let's create a class called Game Event Manager. It contains several methods: subscribe, unsubscribe, and notify subscribers. Notify subscribers method accepts the type of event happening right now, and its only role is to notify the appropriate subscribers. Then, let's create the passive skill interface and concrete passive skill classes, which implement one single method: update. Any concrete passive skill can subscribe to any event that Game Event Manager emits. When the notify subscribers method is called with the event, the Game Event Manager will call the update method for all subscribers listening to that concrete event. Thus, each passive skill will know exactly when it should work. Here, we have 3 actors. The first one, the subject or publisher, is a class that maintains a list of dependent observers and notifies them of any state changes. It provides methods to attach, detach, and notify observers. The observer, or subscriber, is an interface that defines the update method to be called when the subject's state changes. And lastly, concrete observers are classes that implement the observer interface and receive updates from the subject when its state changes. Starting with the benefits, one of the main advantages of the observer pattern is its support for dynamic updates. At runtime, objects can be dynamically added or removed from the list of observers, providing great flexibility in managing dependencies between objects. In addition to this, the pattern ensures efficient communication between objects. Observers are only notified when relevant changes in the subject's state occur, preventing unnecessary updates and helping keep the system efficient. Moreover, the observer pattern aids in maintaining consistency across the system. It guarantees that all observers are kept in sync with the subject's state, ensuring that each dependent object is updated appropriately to reflect the current state. However, there are also disadvantages to consider. Implementing the observer pattern can introduce additional complexity to a system, particularly when there are many observers to manage and their interactions become intricate. This complexity can make the system harder to understand and maintain. Furthermore, if observers are used excessively or the subject's state changes frequently, it can lead to unexpected updates and cascading changes throughout the system. This can make the behavior of the system unpredictable and challenging to debug. Finally, the ordering in which observers are notified can be an essential factor in some systems, and the observer pattern does not inherently provide a way to manage this. This can lead to design challenges and result in code that is hard to maintain. State. Imagine that you are developing a website with a complex registration process. This process should consist of 4 stages: the initial stage, contact information stage, work experience stage, and final confirmation stage. The user should be able to move back and forth across the stages to fill them up. Your main goal is to separate these stages to allow each stage to develop independently. You also want to easily add new registration steps in the future. The state design pattern is best suited for developing this functionality. The state is a behavioral design pattern that allows an object to change its behavior when its internal state changes. It encapsulates different behaviors as separate state objects, allowing the object to move between states while keeping its interface consistent. First, let's create the registration process class, which maintains a reference to the stage object that defines the current stage of the registration. There are also 2 methods, next stage and previous stage. Then, the stage interface defines the methods each concrete stage should implement. In our case, they are the same, next stage and previous stage. After this, let's create the concrete stages: initial stage, contact information stage, work experience stage, and confirmation stage. Each stage knows which one succeeds and precedes it, and we can develop them separately. The overall flow is the following. When the user enters all the required information and clicks the next button, the next stage method on the registration process class is called, which calls next stage on the current stage. The stage itself knows which stage should be the next, and after that, the registration process can perform all required changes on the screen based on the new stage. There are 3 actors in this design pattern. The context is a class that maintains an internal state and contains a reference to the current state object. It delegates requests to the current state. The state is an interface that defines the methods for handling requests. Concrete states are classes that implement the state interface and provide the behavior associated with a specific state. One of the key advantages is cleaner code. This pattern allows you to put different behaviors in separate classes, making the code more organized and easier to maintain. Additionally, it provides flexibility, as the context can switch between other states easily, allowing dynamic behavior changes. Another benefit is adherence to the open-close principle. You can add new states or behaviors without changing existing code. Also, the context code becomes more straightforward and easier to understand, as each state handles its behavior. However, this design pattern also has some drawbacks. It can add complexity, especially when managing many states and transitions. Furthermore, managing the order of state transitions and ensuring correct behavior can be tricky, leading to potential bugs. Strategy. Imagine that you are in charge of creating an image editing application, which should have a feature for applying filters. You are planning on having tons of filters, and now looking for a way to design a filtering engine so that you can easily apply filters on images. At the same time, the filters must be completely separate classes, allowing different teams to develop different filters without changing the application's codebase. For this job, the strategy pattern looks perfect. The strategy is a behavioral design pattern that defines a family of interchangeable algorithms and allows them to be selected and used dynamically at runtime. This also enables algorithms to be encapsulated in separate classes. Imagine that we already have an image class. Let's add a new setFilter method, which accepts the filter interface. The filter has an apply method that takes an image. With that being done, we can create specific filters and set each to our image. Now, completely different teams can work on filters. They have nothing to do with the image class. They just have to implement a filter in the system, and the image will work with all of them in the same way. There are three actors here. The first one is context, a class that maintains a reference to the strategy object and delegates the algorithm's execution to it. The second is strategy, which defines a common interface for all specific strategies. It declares a method for an algorithm. The third one, concrete strategy, is a class that implements the strategy interface, providing a concrete algorithm implementation. The strategy design pattern provides several benefits. This pattern enhances adaptability and flexibility by allowing the algorithms to be changed at runtime without modifying the client code. It encapsulates the algorithms in separate strategy classes, promoting a clear separation of tasks and simplifying maintenance. Furthermore, the strategy pattern ensures that the system remains open for extensions but closed for modifications, adhering to the open-close principle. Despite these advantages, it can introduce additional complexity, particularly when there are numerous strategies and their interactions to manage. Moreover, clients are burdened with the responsibility of selecting and providing an appropriate strategy for the context, potentially leading to an increase in the client code. Template method. Imagine you are writing an application for a bakery that automates the process of baking different types of bread. You realize that the basic steps for baking bread are always the same: prepare dough, bake, and slice. However, the details of each step can vary depending on the type of bread. In this scenario, the template method comes into play. The template method is a behavioral design pattern that defines the skeleton of an algorithm in a base class, while allowing subclasses to provide specific implementations for certain steps without changing the algorithm structure. It promotes code reuse and enforces a consistent structure for closely related algorithms. To implement this in your application, you create a base class called bread recipe that outlines the steps to bake bread. This class contains a method named makeBread, which is the template method. This method outlines the steps for baking bread in a specific order. First, prepare dough, then bake, and finally, slice. We also have some additional methods to provide baking details for makeBread method. In this case, these are getSize, getGrainType, getForm, getTopping, doSlice. However, the bread recipe class does not provide the implementation for these details. Instead, it declares these step methods abstract, meaning the subclasses will need to provide their implementation of these methods. Then, you create subclasses for each type of bread. For now, let's take wheat bread recipe and rye bread recipe. Each of these subclasses inherits from bread recipe and provides its implementation of the details. For example, the white bread recipe might include specific ingredients and baking times unique to white bread. When the user needs to bake a specific type of bread, the application creates an instance of the corresponding subclass and calls its makeBread method. This method executes the steps in the predefined order, but the actual details of each step depend on the implementation in the subclass. There are only two actors in this design pattern: abstract class and concrete class. The first one is the base class that defines the template method and outlines the algorithm structure. It may also provide default implementations for some steps. The concrete class is a subclass of abstract class that provides concrete implementations for the steps defined in the template method. One of the key benefits of this pattern is code reuse. It promotes efficiency by enabling various subclasses to share a common structure. Additionally, it offers flexibility by enabling subclasses to override specific steps or provide different ways of implementing certain behaviors. This is further supported by its ability to separate the high-level algorithm from the specific implementation details, ensuring a clear organization of concerns. However, there is also a significant drawback to using the template method pattern. Its maintenance can become very challenging. Changes to the base class impact all subclasses, so managing and updating the code without affecting multiple application areas can be tricky. Visitor. Imagine that you are developing a strategy video game with several units: archers, cavalry, and spearmen. Each unit can perform actions like attack, defend, move, and so on. You want to implement the same action across all units without having to change the unit classes each time. Also, all the logic must be encapsulated, and addition of new units and actions must be also implemented seamlessly. The visitor pattern is the best for this problem. The visitor is a behavioral design pattern that allows you to add new operations to existing classes without modifying their structure. It separates the operations from the classes they operate on by encapsulating them in visitor objects. This pattern is handy when dealing with a structured hierarchy of classes and multiple operations that need to be performed on those classes. First, we define a unit interface representing all types of units. This interface includes a method accept, the key to the visitor pattern. Next, we have concrete classes for each unit type, implementing the unit interface: archer, cavalry, and spearman. Now, we define the unit visitor interface. This interface declares a visit method for each type of unit. We then create concrete visitors for different actions. For example, in an attack action visitor, we should define how particular units attack. Finally, you can use a following pattern in your game. Here, each unit type can accept different actions, for example, attack, without altering their classes. There are 4 actors in this design pattern. First, the visitor interface, which declares the methods for each element type in the hierarchy. The concrete visitors are classes that implement the visitor and provide implementations for its methods. The element interface declares the accept method, which accepts the visitor, and the concrete elements are classes that implement the element interface and its method. They receive the visitor and delegate the visit to the appropriate visitor method. One of the key advantages of the pattern is the separation of concerns. It separates operations from the element classes, enhancing clarity and maintainability. Additionally, it's highly extensible, allowing new operations to be added without changing existing element classes. This aligns with the open-closed principle, as adding new visitors and operations doesn't require modifying existing code. Moreover, the visitor facilitates double dispatch, enabling the right method to be called based on both the element and the visitor. However, there are drawbacks. It can add complexity, especially when there are many elements and visitors to manage. Another issue is the potential for code duplication. Similar operations on different element types might result in repeated code when multiple visitors are implemented. Furthermore, its applicability is limited. While it's highly valuable for complex structures and numerous operations, it may be excessive for more straightforward situations.